Alright, let's get started again. As you probably could sense, the part about costs is not my favorite. On the other hand, the part about microsimulation and probabilistic sensitivity analysis is. So hopefully I'll do a better job here. These two concepts account for or help us understand the uncertainty that's inherent in cost-effectiveness modeling. It doesn't solve all uncertainty or doesn't help us understand all uncertainty. As I mentioned before, for example, the structural uncertainty, that means the way the model is designed. These two types of like additional analyses don't really tell us much, but they can tell us, microsimulation can help us understand the stochastic uncertainty, which means, so for example, if we estimate on some sample in the past that the probability of getting the flu is 25% in a year in our elderly population, it doesn't mean that the next year, even if like the underlying systemic process will be the same, that exactly 25% of people will get the flu. Maybe it will be a little less, maybe it will be a little more. And this, to understand how much the results can change, that's what we that's when we apply microsimulation. I will demonstrate that in a second. But before I do that, let's revisit our example with vaccinations. In this case, I slightly changed the numbers, but just to make the demonstration easier and more illustrative. So now we have 10 people at the very beginning, and the chances of getting the flu are 50%. We don't really need to care about the inpatient outpatient treatment. Let's just stick for the 50-50 chances of getting the flu. So in our analysis before, so what we did is that, so we had 10 people at the very beginning. If the probability of getting the flu is 50%, how many people will get the flu? 5, right? And let me take a deep breath, and now I'll ask you again. So now we have 10 people again. Chances of getting the flu is 50%. How many people will get the flu? 5, exactly, right? It doesn't change, right? No matter how many times we run this type of analysis, in the deterministic sense, we always get the same result. We always get the same ICER ultimately if we use the same cost, same utilities, same probabilities. I'll skip this slide for a second and get back to it. So let's now try this in a stochastic way. And we will do some demonstration with dice. I will need 10 volunteers. I'll just start here. I'll give you a die. I'll give you 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. All right. I believe they should be all 10-sided, but if that's not the case, it doesn't really matter. Let's agree. So I will ask our volunteers to roll the die. If the outcome is, so first look how many sides your die actually has, but I think it should have 10, if I recall. So if the outcome is 1, 2, 3, 4, 5, you will not get the flu. If it's 6, 7, 8, 9, 10, or maybe you have 10, 20, 30, and so on. So if it's 6, 7, 8, 9, 10, you will get the flu. And so let's try it. Roll the die, and if you get the flu, raise your hand. So the higher values are the flu. 6, 7, 8, 9, 10.
8.
So we got 4 people out of 10 who got the flu. Let's try it again. Five. Different outcome, different universe, different hypothetical universe, different outcome. But note that the underlying probability did not change a bit. It was always 50%. We really didn't change any of the parameters. The probability distribution remained the same, but the outcome was different. So we can do this with probabilities, but also costs. They can have some distribution. What we used before was a mean value that was established by some other study. But costs vary, unless it's like one fixed price for a drug. But let's say costs for hospitalization, they vary. Some patients are more complex than others. Utility values vary. As we saw yesterday, especially some conditions, the utility value ranged from 0.1 to 1, a huge variation. So there was some underlying distribution of the values within, ideally, a representative sample of the population. So if we have access to those actual distributions, that's great. But if we don't, we usually at least have access to some parameters of the distribution. Costs tend to be log normally distributed. So if we at least know what is the standard deviation and what is the mean, we can resemble roughly the distribution of costs for a hospitalization, for outpatient treatment, and so on. So if we assign probability distributions to all parameters in the model, and then we ask a computer, now we did essentially like 20 simulations. We had two rounds of 10 volunteers to roll the die. But we can ask the computer to do this, 10,000 times, maybe 100,000 times, to give us a good estimate of what would actually happen what may potentially happen in reality. So what we just demonstrated is called a first-order Monte Carlo simulation. It's a fancy word, but as you could see, it wasn't that difficult, right? Sometimes it's also called microsimulation, because what we were doing is that we essentially had our volunteers sort of like walk through the decision tree one by one, and so we actually did it like all 10 roll the dice immediately. But essentially, what could have happened that I would ask first volunteer to roll the die. We would figure out whether or not he or she got the flu. Then, if they did, they would roll a die again if they got hospitalized or not. And then would just like walk through the tree. And if we did this, many, many times, it would give us a sense of the uncertainty, of the stochastic uncertainty inherent in the model. So in microsimulation or first-order Monte Carlo simulation, the parameter distributions remain intact, like they remain constant. In here we had the probability of getting the flu was 50%. Not getting the flu was also 50%. We didn't change it, and in 2 different trials we got 2 different outcomes. If you do this way too many times, you will get a close estimate of if you use the mean values, because based on law of the large numbers, the values will converge. But we will still get a sense of the variation that is inherent that may be inherent in the model.
When we say the parameter distributions remain intact, but when we make it 50 and 60, isn't it actually changing then?
But we didn't, right? We kept it 50-50.
But isn't that at one time 40% got the flu, another person times 60?
Yeah, well, but the underlying
assumption
the mechanism remained the same, and then we, through the stochastic process on this data generating process, and even the input parameters remained the same, the outcome was different. But what you're talking about, I'll get, essentially what you're talking about is the second order Monte Carlo simulation, which is another word for the probabilistic or stochastic sensitivity analysis, which I'm going to talk about in a few slides. This is just to list all the variables that can be random variables. And actually, this is now when I look at this list is not exhaustive. Definitely, probabilities by definition, like that's a random variable, whether or not you will get a certain outcome. But risk ratios, when they're estimated in studies, that's based on some sample. There's some uncertainty. There's some distribution of there's some confidence interval for the actual true risk ratio or risk difference. Costs are very often random variables with some distributions. So is effectiveness, utility values, and life expectancy. Even though the life expectancy, we can find some average estimates, but what is life expectancy of every single one of us? That's random. That's a random variable. When I mentioned that this list is not exhaustive, technically the discount rate, we don't really know what the future discount rate is going to be. So we can imply or we can impose some distribution on the value of the discount rate. So this part was about a stochastic uncertainty. Now let's talk about parameter uncertainty. We already talked about deterministic sensitivity analyses, the one-way, two-way, multi-way. When we talk about those, we conducted those sensitivity analyses in this deterministic or mechanistic way. We said, well, so what if the probability of getting the flu is not 50%, it's 60? So we would just plug in 60 and do the deterministic analysis again. And it would, if we kept the distribution at 60-40 and did the analysis multiple times in a deterministic way, we would always get the same conclusion. However, if we did it in the stochastic way, we would get a variation. But what I'm trying to say is that all the parameters in the model, so they have the actual parameters can have their own distribution. What if the probability of getting the flu, what if it's not 50%? What if it's 40? What if it's 60? So we can impose a probability distribution on the value of each parameter. And this would be called a second order Monte Carlo simulation. And second order means that in that case, we would, when each of our volunteers would go through the decision tree, in each part, they would roll the die twice. First roll would determine what's the actual parameter. So let's say if we imposed a uniform distribution on the probability of getting the flu, it could be 1/3 probability that it is 30%, 1/3 chance that it's 50%, 1/3 or 33% that it's 60%. So they would roll a die that would determine that would determine the parameter value. And let's say the outcome would be, well, the probability of getting the flu in this case, in this scenario, is actually 60%. Then they would roll a die again to find the outcome, whether or not they actually got the flu. So this type of analysis accounts for the uncertainty in the values of parameters, of the individual probabilities, of the distribution of costs, of effectiveness, and so on.
In deterministic modeling, the parameters are predetermined that it's going to be 50% probability of getting the flu and 50% not getting the flu. And in this, what is exactly happening? Like if you roll the die and you find out that the person has the flu and another person is not having the flu, are the parameters not predetermined here also? Underlying parameters are...
Exactly, the parameters remain the same. In deterministic modeling, let me make a distinction. In deterministic modeling, you can still vary the parameter values. We can change the probability of getting the flu from 0 to 100. But for every value of the parameter, assuming everything else remains the same, for every value, we would get one result, no matter how many times we would run the analysis. In stochastic way, we can keep the parameter values fixed at first, but the outcomes can vary. That's what we showed with rolling the dice.
So we are assuming that it's going to be 50% of the individuals are going to get flu and 50% are not going to get flu in deterministic modeling. But
yes.
What is exactly happening?
In stochastic, we know that there is some flu generating process in this case that on average turns out in an outcome that 50% of people get the flu and 50 don't. But when we roll the dice, it was 40-60, sure. There is this uncertainty so you can think about it, so our parameter, our 50-50% chance of getting the flu or not, is based on some past experience, on some past sample. Whether or not that will replicate in the future is uncertain. And even if essentially like the risk of getting the flu will remain the same, there will be no new virus in the environment. The outcome can actually be different.
Can we ever be certain that there are nothing
Never. Never. You can be never certain with anything. even in life, not only in cost effectiveness.
In this experiment, you must understand that the chances of bias he kept at 50%. So that is why actually it will vary. Chances he kept at 50%. 1, 2, 3, 4, 5 will not get. 6, 7, 8, 9, 10 get. So that is 50% chance. So that is fixed. And actual output will vary.
Maybe a slightly different example. So if you flip a coin, it can be heads or tails. The chance, if the coin is fair, it should be 50-50. If you flip the coin once, it will be one or the other. It will not be 50% of the two, right? If you flip the coin twice, maybe you will get heads and tails, but maybe you will get heads and heads, or tails and tails. So even if we keep the data generating or the outcome generating process fixed, the stochastic aspect introduces this uncertainty that the outcomes just like may vary slightly from the average.
But even in this experiment, if we run this sufficient number of times, we'll come back to being equal.
Exactly. And we'll
number.
The average would converge to the exactly, but we will still get at least a sense of the variation, because even though we will, like if 1,000 of us will roll the die, it will be it will be very close to 50-50. But maybe it would be 498 versus 502. to understand the answer, so what we're trying to do with cost effectiveness analysis is to inform a decision, and inform a decision about something in the future. We build our model based on some assumptions, and even if the assumptions, of course, like the assumptions can change, that's a different problem. But even if the assumptions are actually satisfied, the results may not translate in future outcomes because of this stochastic uncertainty. And so if you're the decision maker, you get the ICER from analysts. And you're like, well, how can I be sure that this will actually happen? This can give us at least a sense.
What is the range? Variation.
Exactly. It will give us some variation. You will soon see like how it can give you some probability estimates of the true value of the ICER. So it's just, we do this because there is uncertainty, and if we ignore it, then we're making a huge mistake. So if we acknowledge, yes, there is uncertainty, even if I make this recommendation, it doesn't mean that it will actually doing this intervention will actually turn out to be cost effective. But I will at least give you some sense how certain I am.
I'd like to know how does it work, for example, in deterministic we saw like in the Excel sheet yesterday that everything is fixed and what is moving from one state to another.
Yeah.
But how exactly is variability in the outcomes produced?
Very good question. I honestly, maybe some people who are better in Excel than I am can do this in Excel. I think
Whichever software.
Yeah, exactly. So I don't actually know how to do this in Excel, but other softwares such as R are good in generating random outcomes based on specified distribution. You can specify, just like for simplicity, you can specify a normal distribution with some mean and some standard deviation. And you can tell R, generate me 10 numbers from this distribution. R will do that. And if you run it again, it will give you different 10 numbers. So you need probably more advanced software than Excel to do this. Yesterday I mentioned the software Triage that's designed for cost effectiveness analysis that can do this very easily. For each parameter, instead of a value, in the Excel spreadsheet, we had a sheet that was called parameters. And each parameter had just one value that was fixed. In Triage, you do exactly the same thing. There's also a sheet that's called parameters, where you specify all the variables, all the parameters in the model. But then you can save a copy and replace all the parameter values with distributions. Once you have these distributions, then Triage can run the model 10,000 times and estimate the variation. You also had that.
So this basically is like giving the confidence interval. Is that what it is?
Yeah. We'll get there in a second. All right. So first order Monte Carlo simulation or microsimulation gives us a sense of the amount of stochastic uncertainty. Now I realize that so when someone here mentioned that in large numbers we will get to the deterministic value essentially. So if our intervention is meant for large populations, then this is not as important. Like if we know that we will implement this intervention for 10 million people, the proportions will roughly work out. But if we're evaluating an intervention for a rare condition, and we know that we will offer this to 100 people. Is this cost effective or not? The proportions, the stochastic uncertainty may totally change the, there may be a much bigger difference in these small populations from what the model predicted and what the reality ultimately was. So that is microsimulation. Probabilistic sensitivity analysis, sometimes called stochastic sensitivity analysis, or second-order Monte Carlo simulation, takes this one step further, because even the parameter in our demonstration, it was the 50% of getting the flu, is uncertain. And we would first roll a die. Well, so that 50% parameter would also have its own probability distribution. And we would first roll a die to figure out first the value of the parameter, and then based on the parameter, we would figure out the outcome. That would be the second step. And one critique of this is that, so what should be the distribution of a parameter? By essentially assuming, well, this could be a normal distribution, brings in another level of uncertainty. And so some people would argue against doing probabilistic sensitivity analysis. Just letting you know. I think if you carefully think about how the parameter would actually behave, if you select an appropriate distribution, this really can provide a lot of value to the decision maker to understand the uncertainty in their decision. So some of the distributions usually selected for parameters is costs tend to be very often log normally distributed. For probabilities, because probabilities are bound between 0 and 1, you cannot really use a normal distribution, because there is even if you specify it narrow enough, there's always a teeny tiny chance that you will get a value that's outside of this range. So in that case, either a uniform distribution that can be bound between two values, or a triangular, which has a shape of a triangle. Sometimes beta distribution is used for the distribution of probability parameters. But it depends. It depends on how rare the event is and how much data you have about each individual parameter value. So I highlight that always make sure that the distributions of the parameters will generate plausible values, such as you don't get a negative probability.
Could you just explain the second order Monte Carlo simulation with the die thing that you said? Roll it twice, why you said that?
Yeah, so in the first demonstration, the probability of getting the flu was 50%. It was fixed. And you only rolled a die to figure out what the outcome would be, whether or not you get the flu. There is a good chance that I'm not so sure that 50% is a precise estimate of the probability of getting the flu. So I can impose a different distribution on those 50%. And I can say, well, maybe the probability varies between 30 and 70%. It's somewhere in between. And let's say for simplicity, let's assume a uniform distribution between 30 and 70. You would roll a die, and based on the outcome of the die, you would find the appropriate value of the parameter, and let's say it would point to 60% this time. So that would be the first roll. Now all right, so this random process told me that right now my chances of getting the flu are 60%. Then you roll the die again. But in this case, you wouldn't look for 1 to 5 versus 6 to 10. you would look 1 to 6 versus 7 to 10, which would then determine your outcome. So that's like essentially you would, for each step, you would roll the die twice. First, we'll figure out the distribution, and then the outcome. Sure.
The parameter distributions.
Here. Yes. So how do you decide like what distribution should you impose on every of the parameters of your model? You have utilities, you have costs, you have probabilities. You even have a discount rate. What is an appropriate distribution for every single one of them? So you just like have to, well, ideally, if you have empirical data, real data, you can use the empirical distributions and draw random values from there. That is one option. But in many cases you don't. For example, you know that the utility value, the average utility value is 0.8 and the standard deviation is 0.1. So what distribution would you pick? Maybe, but you also know that a utility value is also bound between 0 and 1. So maybe you should be careful. Like if you picked a normal distribution, you know, more than 1 is only 2 standard deviations away. So there's a chance that at some point you would draw value that's outside of the plausible range. So you just like have to think about what's appropriate. In this case, maybe a uniform distribution would make sense. Maybe a triangular, maybe a beta distribution. You just like need to know all the various shapes of distributions that are out there and their properties.
Says statistics in literature is mean and standard deviation. So if costs are skewed, not normal, then should we not use median and interquartile range? Right?
Absolutely. If you have those available, then absolutely. Because the median on the skewed data will transform to the mean of the log normal distribution. And then it will work out. So it always depends, like what statistics do you have available. If you have the shape of the entire distribution, just use that. Just use the empirical distribution. You can do that. For example, in Triage, you can import data, actual data, for example, of costs. And then Triage will use that empirical distribution to draw values from. But in many cases, you will have only some summary statistics from published papers. If they reported for costs median and interquartile range, well, not really the range, you actually need the quartiles, then sure, use that because that's a better measure of, better description of the skewed distribution. If they reported only a standard deviation, then you just have to deal with it.
What is bootstrapping?
Bootstrapping means that from your sample, you take smaller subsamples and estimate the result of whatever analysis you're doing on the small subsample. And that will also give you some sense of the variation in the data and of the result.
So, which sensitivity analysis should be done in what circumstances?
So, the probabilistic sensitivity analysis, or in other words, second order, it already incorporates the microsimulation. So, in my well, not only in my opinion, even in the opinion of the panel on cost-effectiveness analysis that published the book I talked about before, the recommendation is that every cost-effectiveness analysis study should do a probabilistic sensitivity analysis. And let me also mention that, so when we talked about the deterministic sensitivity analysis, we talked about one-way, two-way, and multi-way. You technically can do one-way, two-way, or multi-way using the probabilistic sensitivity analysis, but in most cases, you do only the multi-way sensitivity. Essentially, in the probabilistic sensitivity analysis, you assign distributions to all parameters that are uncertain. And then just, let the computer do the work. And that gives you a really good sense of what can actually happen in the real world. So the outcomes, as I already mentioned, it gives you an estimate of the overall impact of uncertainty on the results and conclusion. It gives you probability distribution of total costs, total effectiveness of each strategy. It can give you a distribution of the ICER. Then you can calculate a 95% interval, confidence interval for the ICER. The results are typically presented as a scatter plot of incremental costs and utilities, and or as cost effectiveness acceptability curves, which is, and I'm going to talk about all of these right now. So let's keep going. So this is just an example like how we could vary, all the parameters, and so I can skip that. This beautiful thing is a scatter plot of total cost and total effectiveness of our two interventions. Vaccinations are the red dots, and blue dots are no vaccination. And this, even though it looks pretty, you can put it on a wall in your office, this doesn't tell you much. What it tells you more is if you do the scatter plot of incremental cost and incremental effectiveness. In this case, the reference is no vaccination, and it's always, for each trial in our probabilistic sensitivity analysis, which we ran, in this case, maybe 1,000 times. In every trial, it calculated the total costs, the total effectiveness for both strategies, then it calculated the incremental cost and incremental effectiveness. So you essentially have a data set that has 1,000 different incremental costs and 1,000 different incremental effectiveness measures. When you plot them in this way, this is our cost effectiveness plane, right? Remember the sun, when we looked at it, if it's in this quadrant or this quadrant or this quadrant. When we talked about that plane, interventions in this quadrant were dominant. They're cheaper and more effective. In this quadrant, they're dominated. They're more expensive and worse. This quadrant, they're better but also more expensive, and so on. So now you actually, so also what I should mention, this is our threshold. In this case, I set it at $20,000. And if we were to increase the willingness to pay threshold, it would still be, it's fixed at 0, like there's like a pin here. And if we increase the willingness to pay threshold, it will become steeper. If we decrease it, it will become more flat. And now what can happen? So once we have this line, we can of the total 1,000 dots, all the dots that are on this side, we can count them. The computer will do it for us, but we could technically count one dot after another. So the proportion of dots on this side will tell us this is the probability that our intervention, vaccination, will be cost effective at the willingness to pay threshold of $20,000 per quality gained. If we rotate the willingness to, or if we change the willingness to pay threshold, we would rotate this line, and so the number of dots would change, probably. So at different willingness to pay thresholds, the probability of the intervention being cost-effective will change. In a similar way, all the dots on the left-hand side, that's the probability that the intervention will not be cost-effective at this particular willingness to pay threshold. We can also calculate all the dots in the bottom right quadrant. That's the probability that the vaccination strategy will be dominant, will save us money, and improve health. Same way, there is also some probability that the vaccination will actually cost us a lot of money and people will be worse off. So, when I talked about this graph, when we can calculate what is the probability of the strategy being cost effective or not. So now we can like plot it. Like in this case, at this 20,000.
Can you go back to the previous slide, please? Yeah. Why this willingness to pay line is at an angle?
The angle is So we are willing to pay $20,000 per each additional quality gained. So this is incremental effectiveness. So for 1 unit, well, we actually never get to like full 1 quality here, but for 0.01 quality, we're willing to pay 20,000. So that this would be what, 200, right? And at this point, like, we should roughly get here to 200. So it's essentially a function, because the willingness to pay threshold is cost per quality. Therefore, it's a line on this plane.
So if it increases, then it becomes the angle also, angle lessens.
If it increases, then it will be steeper. Because for each additional unit of health, you're willing to pay more.
Please repeat.
The willingness to pay threshold, if you increase your willingness to pay.
How did you arrive at the position?
Yeah, so we know that our willingness to pay is $20,000 per quality gain. So if we gain, we don't have, like, this is just 0.01 quality. So for 0.01 quality, we're willing to pay only $200 because that's 1% of 20,000. So for this one unit increase, we're willing to pay 200, which is here. For 0.2 units, we are willing to pay 400, but that's all the way up in the air conditioning here.
Second order. This scatter is brought about by second order model.
Yes, this is second order. All right, so yes.
I just had a doubt. In the second order, the stochastic part is also there with each parameter estimate.
Yes.
So there's a parameter variability and stochastic.
Yes. Even like figuring out what the actual parameter value is figured out in a stochastic way. That is when you roll the die to figure out whether the probability of getting the flu is 30%, 40, 50, 60, or 70.
So second order particle takes care of both the
Exactly. All right. So from these two graphs, we can calculate at our given willingness to pay threshold, which is $20,000. The number of dots divided the total number of dots would be the probability of the intervention being cost effective. The number of dots in the red shaded area would be the probability divided by the total number of dots would be the probability of this intervention not being cost effective at the 20,000 willingness to pay threshold. So for willingness to pay threshold of $20,000, we can plot them, right? So we have 94.5% chance. If we're willing to pay $20,000 per quali gain, we have 94.5% chance that our vaccination program will actually be cost effective, and 5.5% that it will not be. And the thing is, because the threshold is very often somewhat uncertain, we can do this type of analysis for different thresholds. We would rotate the willingness to pay threshold back and forth, and it would lead to different probabilities of the intervention being cost effective. And when we do this, we get what is called an acceptability curve. On the x-axis, we have the willingness to pay. And for each, essentially, each spot on this continuum, we calculated the probability of the vaccine program to be cost effective or not. If we were willing to pay, if we were essentially not willing to pay anything for a quali gain, the chances of the vaccine program to be cost effective. In other words, we are hoping that the program will be dominant. It will save money because we're not willing to pay a penny for additional quali gain. But there is a chance that the program will actually save us money and make people better off. So that probability is 30%. Not negligible, but also not high. As we are willing to pay more for additional quali gain, the red triangles, that's the program, we're increasing the chance that we will deem it cost effective. Obviously, the blue line is just the inverse of the red one. Are your brains exploding?
Blue line starts at 70%.
Yeah, so if we're not willing to spend not a single rupee for additional quality, there is a 30% chance that the program will save us money and make people better off, and 70% chance that it will not.
That is one.
Yep.
So ours showing 20,000 is at 94, and people made it.
Exactly. So here we found that at $20,000 is 94.5. So if we look here, we are roughly at 94.5.
But why did this thing come down?
I'm sorry?
Why did no vaccination curve come down?
They are complementary, right? If we have a 30% chance that the vaccine will be cost effective, that means 70% chance, that means there's 70% chance that it will not be cost effective. And if it's not cost effective, then no vaccination is.
So complementary.
Yeah.
100 minus, blue line is 100 minus the red line.
Yeah. Honestly, I think it would be much easier if the blue line just wasn't there. It just makes it confusing, but they're symmetrical.
So this basically can tell you how much you actually need to pay, beyond which there's not much benefit.
In a way, yes. If you want to be certain, that you will have a good feeling that you did a program that's cost effective. If you want to be pretty sure, you need to be willing to pay a lot of money. But that still doesn't help us allocate, resources efficiently. Of course, if you want to be certain that it will be cost effective, you just have to be willing to spend anything.
No, what I was asking is, from this graph, after 10,000, it seems to kind of plateau off. The incremental gains is what's or the probabilities can plateau off. So even if the willingness to pay threshold is around 10,000, it still would have a good amount of
Gains.
Yeah, so after a certain point, in this graph, no matter how steep we make this line, there will be still some dots in these areas. And so even if we are willing to spend like essentially anything possible, infinite amount of money, it may still not be cost effective. Like we will never reach the 100%. In this case, if all these dots, essentially if we shifted all the dots a little bit to the right, it might be, a different kind of intervention might be, but this intervention has some chance, based on the parameters, based on our model, there is still some chance that we will spend money and hurt people. So even if we're willing to spend anything, we may not be certain that the program will definitely be cost effective.
Next. So this blue bar represents all the dominant sites, right?
Not necessarily dominant. It represents all these dots. All these dots in this green shaded area, because in here, so it includes all the dominant. That means like all the potential scenarios when the program is saving money and making people better off. But it includes all the scenarios where the program is making people better off, but costs money, but not too much. But it also includes two potential scenarios when it's actually making people worse off, but also saving a lot of money, which we also may have.
So the cost effective.
Yeah, like if we may be willing, like this can be an example of much cheaper vaccine but giving people a rash. So we may be like, well, like if people get rash, that's okay. If we save a lot of money, we can spend it on something else.
Many times, 94.5%.
Yeah, it was like, so the number of dots in this area was 94.5% of all the dots in this figure.
The question was that changing the threshold, I guess, was if you reduce the willingness to pay threshold down to 10 or 9,000, in that graph you still get a cost effectiveness of 90%. Let me say, well, that's good enough, so why don't we just spend that much?
You will, no matter what, like if you decide to implement the program, it will cost the same amount of money. Like if you, so in here, find out that it actually was not.
This can be taken from individual perspective. I am paying for flu vaccine. Can this analysis hold?
I generally want to think about cost effectiveness analysis more of a population level and policy level type of analysis. However, technically yes, like it gives you the expectation. Like if you, now you will see your chances that if you spend the money, if it in the expectation, if it will be money well spent. Like what are the chances that it will or it will not?
Suppose if the willingness to pay is $10,000 for 12, what will happen to that? Like
it will be more flat. It will, so
to the left or right?
This way. So this line, the willingness to pay, is fixed at this point. And so for 0.01 unit of quality, suddenly you're willing to pay, if it's 10,000 per quality gain, so for 0.01 you will be willing to spend only 100, which is here. So the line would go this way.
What does the circle mean?
That is something what TreeH does, and I don't really know what that is. It's probably like where a majority of the dots are. But, yeah.
And this can be done only with TreeH.
So, no, you can do this in R, but 3H is a clicky thingy, like fairly user-friendly software, and you can only like click a button that says second order Monte Carlo, as long as you already assign the distributions, and it will spit out these graphs automatically. If you do this in R or C++ or whatever other programming language, you will generate the data and then you will have to plot them yourself, but you would get the same figure. Maybe like the graphics would look differently.
On the reverse side, can we determine the willingness to pay based on the acceptability curve?
I don't think so. Yeah. Like how would you do that?
Make the curve plateaus off.
Well, but that's for one intervention. Different interventions may have totally different acceptability curves. So this is not a way how to, like, willingness to pay threshold should be decided ex ante before you start the analysis. And we will talk about that in a second, how that's actually done or can be done. It can be totally just like, I think our willingness to pay threshold is this. Like if you're the decision maker and the budget holder, you can decide on, based on your feeling. But there are also ways how to estimate societal willingness to pay thresholds.
The sensitivity analysis is only for model-based. For trial-based, if you're doing, there is no...
Yeah, like in trial-based, you just follow patients and you see whatever happens. There's not much you can do. Let's go there. And
can we go to the next slide where you have the red line? Yeah, okay. So the red curve looks very much like ROC curve for a diagnostic test evaluation. So can we make use of this to get the best cutoff, which will be left upper corner of the curve, and then we say, okay, this is the best cutoff for the willingness to pay, and we should be willing to pay only this much to get the best effectiveness.
Well, I cut it at 40,000, but unlike ROC, which is bound between 0 and 1, this can go to infinity. Like this willingness to pay can, go all the way. I just like for...
Yeah, but there are no extra gains, it plateaus.
Well,
plateaus.
but this is...
Choose the left upper corner.
So this is only for this one particular situation. A different kind of analysis, different kind of intervention, different kind of model. This line can actually, it doesn't always have to go up. It can go down. It can change shape. Like there are many different shapes of acceptability curves. So even though like this particular one kind of resembles an ROC curve, it's not the same thing.
My question was, what do we do with the acceptability curve? Are we there? Are we saying that it's only above this, that is like a cutoff?
Yes, so I think the main reason why we have the acceptability curves are policymakers in countries such as the United States, where there is no single entity that would be willing to step forward and say the willingness to pay threshold for a quality gained in the United States is this much money. So this can give you a sense of what is the probability of the intervention being cost effective, depending on whichever value you decide is your willingness to pay threshold. And you can, for example, you can maybe present this to different entities, and maybe they have different willingness to pay thresholds. Or maybe some entities, are not willing to decide on the willingness to pay threshold at a particular point, but they may be willing to give you a range. They wouldn't say our willingness to pay threshold is 400,000 rupees per quality, but they could say like, we feel that somewhere between 300 and 500 is about appropriate. then you can look, all right, so now in this case, maybe they would say 20 to 30,000. So we would look, well, within this interval for willingness to pay threshold, chances are pretty good that this intervention will be cost effective. So it just like releases the pressure on the decision maker to put one strict cutoff line that decides everything.
The scale, the willingness to pay 5,000 to 10,000. The scale may be wide range. If you increase the scale like 5,000 to change it to 100 scale, then again this graph will go suddenly up.
Yeah, like if you rescale this, then the shape will be slightly different, but it will still like describe the same relationship.
I'm thinking the policymaker will not willing to pay suddenly double the amount. They will increase that willingness to pay.
Sure, like of course, like this.
Suddenly they will double the. For example, now I'm spending $100,000. I can't willing to pay another $200,000.
Yeah, if you know that there is no way the decision maker would spend more than $100,000 per equality.
But here, the willingness to pay should be 500,000. Then it is increased to 90%.
Sure. Like I could have made this graph longer, but for educational purposes, I believe this illustrates
the reality. Maybe the willingness to pay will go slowly.
In this case, yes. In this case, it really like the more you're willing to pay, it converges. It gets closer and closer to 100, but it will never reach it. And it will never reach it because we have at least some dots that would cost us money and harm people.
So can this graph inform policymakers to reduce the willingness to pay?
No.
If they're willing to pay more?
No.
And this can help?
No. The willingness to pay should really be decided ex ante. This graph, this graph really is only for our vaccine program. And if we looked at a drug for, decreasing blood pressure, the acceptability curve would look totally different. So this only releases the pressure from the policymaker to say, here's a strict line. And if you're slightly below, we'll pay for that. If you're slightly above, we will not. It gives them the option to say, like, this range seems fair. Of course, there is still, like, even the range has an endpoint, right? But it at least gives them some option to not specify, like, one strict cutoff. And maybe let me take a step back here. What I talked about at the very beginning. So, cost effectiveness analysis is a tool that is designed to help with complex, complicated decisions. It can inform the decisions. It synthesizes evidence. It gives us, it gives us some insight what may be happening, but it shouldn't be the sole, one and only thing that we consider when making these decisions. Because these acceptability curves could show us that killing old people is cost effective. We shouldn't do that. So this is just like one tool that gives us a sense, all right, at different willingness to pay thresholds, what are the chances that we will spend our money wisely? There will always be uncertainty. Maybe if we spend this money, maybe it will turn out as a disaster, but we don't know that. But this at least gives us a sense of how confident we are that it will not be a disaster. But there are still other things that we should consider. in making the final decision whether or not to implement the program. So the red line tells us what's the probability that at each point it will be cost effective. So in this case, when it's like here, it's 90% chance that it will be cost effective. That means that there's 10% chance that it will not be cost effective. If our alternative is no vaccination, the 10% chance of vaccination not being cost effective means 10% chance of no vaccination being cost effective. So it's just like these two, like if you put a mirror in here at 50%, they're exactly the same. All right, let's see if I have some. Oh, I have one more graph. You can also generate a distribution of the ICER. This one is not that informative. It seems that there is a wide variation. That there are some. In our simulation, we found some hypothetical universe where the ICER was insanely high. $700,000 per quality, but the chances are pretty low. With the distribution of the ICER, you can also put a 95% confidence interval at the 2.5 and 97.5 percentiles. That also gives you a good sense how reliable your estimate of the ICER is. Obviously, the more variation in your parameters, the more variation in the ICER. So if you can get good estimates of your parameters, the more reliable your model is going to be.
This is my second order of evaluation.
Yes, yes.
But what is the problem with refixing the willingness to pay once you have got that graph?
Well, if you can adjust the willingness to pay threshold, why bother doing this analysis in the first place?
We started with a certain number, but we found something else. So does it not?
So let's say at first we decided, well, we're willing to pay $400,000 per 400,000 rupees per quality gain for our intervention, and then you do the analysis and found that it's 1 million rupees per quality gain, and then you're like, that's fine. So what was the reason? Why did we even try to if you want to do the intervention, no matter what the cost is, then just do it. You don't need this kind of analysis.
But it is of advantage when it is lesser, isn't it?
It is, but if you're willing to adjust your willingness to pay, that means that you're willing to pay pretty much anything.
So here they're changing the probability and drawing the graph, right?
I'm sorry?
Changing the parameter probability, right? Like a 50% to 40% in range.
Yes, so the probabilistic sensitivity analysis, we did that 1,000 times. In reality, I think in this case I did it 1,000 times, but normally, because we have strong computers, people do it 10,000 times, maybe 100,000 times. So you would get essentially 100,000 different ICERs for each hypothetical universe or alternative universe. And then you plot them, these 100,000, then you plot this is essentially a histogram of the different ICER values that each simulation generated. And you can see that most of the ICERs are, most of them are here, slightly are positive, That means that the intervention costs money but also is effective, or at least saves money. But also like a lot of isotopes were negative. That means one of the interventions was dominant and the other one was dominated. This still doesn't tell you which one it is. So you should, use the acceptability curves in addition to these distributions. All these graphs can give you a sense of the inherent uncertainty in your model based on the uncertainty in the parameters.
The willingness to pay for the security depends on the health system's willingness to pay. But in most of our cases, it's actually the patient who pays out of pocket. In which case, shouldn't we be able to vary and readjust the threshold at which the willingness to pay is set, so options are clear?
So as I said before, I really think cost effectiveness is really mainly for policy type of decisions, these like population studies. But even from the patient perspective, every one of us have different willingness to pay threshold. We value the quality of life differently. We have different incomes, different amount of savings. So willingness to pay threshold varies by person. So you could actually show this to your patient and be like, well, what are you willing to pay to improve your life? If you're not willing to pay much, then your chances, if you spend money on this vaccine, or in a different example, like if you spend money on this procedure, on this drug, it may not be, if the chances are low, it may not be wise. But if some other patients may be willing to spend much more, and then you're like, well, if you're willing to pay this much, I think you will spend your money well.
Can this graph be used by the pharmaceutical companies while fixing up the prices of some of the drugs or vaccines?
I'm pretty sure they do that. They're fixing them like towards the upper end though. Alright, so one more thing that I would like to stress out. I noticed that in the past, when I taught this to MPH students, some of them confused the cycles in the simulation with cycles in Markov models. Those are conceptually different things. Or the trials in the simulation with cycles in Markov models. If we were to do a probabilistic sensitivity analysis on a Markov model, in our example that we worked on yesterday, there were 30 cycles. So one trial, one simulation trial, would mean going through all 30 cycles until we would get the ICER. We would record that ICER on the side, and then we would run another trial through all the 30 cycles until we would do this 10,000 times or 100 times. So yeah, but like computers these days can do this within minutes, maybe hours, but it's still usually very manageable. So I just wanted to stress out that cycles in Markov models and trials in a simulation are two totally different, conceptually different things, and should not be confused. Maybe another way how to say this: a cycle in a Markov model represents some period of time that we decided on. We decided on the length of the cycle. In the exercise yesterday, we decided it's 1 year, while a trial in a simulation is one alternative universe, and we would see how that particular intervention unfolded in that alternative universe. And another trial is a different universe. So this is really important. And by the way, the cycle length and time horizon, that is something that you can actually vary as well, to make sure that the results are not driven by the particular cycle length that you selected. And that's all I have for this session, so there are questions.